Welcome to DVCON 2022. I'm Debarshi Chatterjee, and today I'm going to present BatchSolve, a divide and conquer approach to solving the memory ordering problem. This work is co-authored by Ismet Beratuglu, Nikhil Sathe, Kavya Shagrithaya, Siddhant Dodi, and Spandan Kacharia. Memory ordering problem arises frequently in memory subsystem test benches. Let us first understand what this memory ordering problem is. The memory ordering problem aims to find out if there exists a global order given the issue order of memory operations and a bunch of ordering rules. Let's take the example on the right to understand this problem better. Let's suppose that we have two sources, source 1 and source 2. These sources could be threads in a multi-threaded program, or they could be BFMs driving memory operations on interfaces. So let's suppose source 1 drives two stores, store 1 and store 2, with data X and Y to the address A, and source 2 issues two loads, load 1 and load 2, and receives data X and Y again to the same address. Now, since load 1 gets store 1's data and load 2 gets store 2's data, to an external observer will infer that load 1 must be ordered after store 1 and load 2 must be ordered after store 2. And so based on that, there are two possible global order that an external observer can infer. Now let us suppose there is a ordering rule which says memops from the same source must appear in global order in the same order as they appear in the issue order. So if this rule has to be obeyed, then you can see that the second global order does not obey that, because in the second global order, store 2 is ordered before store 1, whereas in the issue order, store 2 is ordered after store 1. However, there exists one global order which satisfies the observation of the load data and also obeys the ordering rules. So we will call this execution a legal execution. However, if keeping the problem same, if the loads got the data in the reverse order, then you could see that there are two possible global order, but none of them really satisfy the ordering rules. So this kind of execution we will call an illegal execution. As verification engineers, our job would be to run tests, find out if there exists a global order subject to all the ordering rules, and if there's not, then we'll file the bug. And where are these ordering rules coming from? The ordering rules are mainly guided by memory consistency requirements. They could also be arising from deadlock avoidance rules, and usually they are spec'd out in the architectural specifications. There could be link-based ordering rules and so on. The memory ordering problem is very similar to the memory consistency problem, which has been studied thoroughly and is known to be NP-complete. However, there are some differences between memory ordering problem and the memory consistency problem. The memory ordering problem arises in memory subsystem test benches at unit level and integration level, where the BFMs are driving memory operations on the interfaces and doesn't have a direct notion of program order. Moreover, the memory operations that we are trying to order here could be partially overlapping reads and writes, or writes with byte enables hosts, things that are not common in memory consistency problem. And finally here, the ordering rules are guided not just by memory consistency requirements, but they could be ordering rules coming from deadlock avoidance. Although there are differences and similarities, for prior work section, we're going to discuss approaches which have been used for memory ordering problem in the industry at NVIDIA and elsewhere. So there are two main very popular techniques. One is the point of serialization snooping technique, which is known by other names in different places. But basic idea here is you're driving memory operations on the DUT, and you track each and every memory operation inside the design using monitors all the way to point of serialization. And then we basically get hints from the RTL to figure out how the design ordered these memory operations instead of inferring the memory operation order. So this works very well because there is no assumption in terms of there's no stimulus restriction, and this can be done in linear time complexity. The disadvantage is that this method is extremely difficult to port over to different test benches, and also since we are tapping internal RTL signals, any changes to the RTL can cause changes in the tracking logic or serialization code, and so which makes this a very high development and maintenance cost. The other approach is TSO tool approach, in which this approach uses an assumption that every store has unique data. And so this can be created by just incrementing the store data. So because every store has a unique data, every load will get the store data from a unique store. And so we could draw edges from store to load. And the basic idea of TSO tool is we consider every memop as a vertex in a graph, and we draw edges based on the issue ordering rules, and also edges based on what the load values were observed. And then there is a notion of inferred edges, which I cannot go over in details in this presentation. But the idea is once you draw these edges, we will do a cycle analysis on the graph. And if a cycle is present in the graph, as in this case, then that execution is illegal. Again, this has reasonably good coverage because the assumptions are very limited, and this can be done in polynomial time complexity. However, because of the unique store data requirement, it's very difficult to handle random atomics, and also this method is not very amenable to arbitrary ordering rules. That is, if you have complex ordering rules like PCI ordering rules or other link-based ordering rules, then taking that and generating rules which will generate the inferred edges is a non-trivial problem. The motivation for this work is the need to develop an ordering checking scheme which is portable, low cost, and flexible. So we want this checker to be extremely versatile, as in it should be amenable to various ordering rules like PCI, NVLink, or other ordering rules, and it should be easy to change these ordering rules. And we also want this checker to have very low development and maintenance cost. So at a very high level, the idea of BatchSolve is to specify ordering rules as high-level system Verilog constraints, and then formulate this problem so that the system Verilog solver can handle it. But since it's an NP-complete problem, as the number of memops increases, the ordering to find out global order using the solver scales exponentially. So how do we address this scalability issues? And we do it through something called stimulus batching. In subsequent slides, we'll first discuss how stimulus batching is done, and then we will discuss how we can formulate this problem so that the system Verilog solver can solve it. This slide shows how BatchSolve can be integrated in the standard UVM architecture. The diagram on the left shows a standard UVM architecture. The diagram on the right shows how BatchSolve is instantiated in the scoreboard, and it has a stimulus API. Every sequence in every agent will have a stimulus API to talk to the BatchSolve. So when the sequence generates a memory operation, before sending it to the driver, it will ask BatchSolve for permission regarding sending it to the driver. If BatchSolve says yes, it can send it to the driver. If BatchSolve says no, it will need to re-randomize the memory operations, ask for permission again before sending it to the driver. And this is the mechanism by which stimulus batching happens in BatchSolve, which will be discussed later. But the idea here is BatchSolve basically gets queries from multiple sequences, and it either grants or denies, and by doing so, it acts as a stimulus filter. Okay, so this slide demonstrates a sample output of the stimulus batching code that's there in the bats. So using two addresses X and Y, here with each arrow represents the drive time of a memory operation on the DAT boundary from a source. So as you can see, when various sources start requesting a particular address X and drive them on the interface, for the first few requests, the agents will ask bats for permission to drive this, and bats will, for the first few requests, the bats will grant permission, but it will keep a total count of number of requests sent by all the agents to the DUT. And once that count reaches a certain threshold, then bats internally transitions this cache line state to an almost full state. And what it means, when the cache line transitions to an almost full state within bats will start denying any request to that cache line for a simulation time delta. After the simulation time delta, if any agent asks for the same cache line, it will give conditional grant. And what that means is that the agent should be able to drive um, a full cache line read to it. And once it does that, the batch will transition this cache line to to a full state. Again, what that means is in that full state, batch will not grant any access to that cache line X for a sim time delta. Once that sim time passes, it is good to other agents are again free to reuse that cache line X. One thing to note here is that once a cache line goes into a full or almost full state and bats start denying requests to that cache line, the agents are free to re-randomize the item and generate another address and drive onto the DUT. So by this mechanism, basically bats spaces out requests to the same address from various sources by a certain simulation time, and creating effective batches of addresses, batches of requests to the same address. And because they are spaced out in sim time, if the sim time spacing is sufficiently large, then there is no racing across the requests in different batches. And so we can use the solver now to find the geo across each of these batch and concatenate the geos from the solver to find the final geo across batches. Another way to visualize this stimulus batching mechanism is using this tabular structure. So BatchSolve would maintain a table per cache line, and as various sources sends requests to the cache line, it will put each request or memo in a separate row. So for instance, the first row is saying that at time t1, source 1 made a request which is of type write, and the write basically wrote the first 3 sectors of the cache line. So initially the cache line is an empty state, and BatchSolve keeps granting permission to write to the cache line, but it keeps incrementing the count. And once the count reaches batch size -1, it will go into an almost full state. And from that point onwards, between T9 and T10, it will deny any request to access this cache line. And if after that simulation time threshold passes a threshold delta, it will access a conditional grant, meaning anybody trying to access the cache line can only issue a full cache line read. And we call this a space read. So basically the last request to a cache line in a batch will be a space read. And the reason being so is the reason we need a space read is because we will use the read data returned by the space read as the initial value of the memory for the next batch. So for the 0th batch, we know the init value, but for the batch 1, we don't know the init value. And by issuing a space read, we make sure that the space read does not erase with any of the prior transactions or with the second batch transaction in the other batch. So its value can be used as the init value for the subsequent batch. Now that we understand how the stimulus batching happens, let us now focus on how we present the batch to the solver and ask the solver whether there exists a global order subject to ordering rules. So to do that, since the ordering needs to happen at sector level granularity, we take the previous table and filter out everything other than transactions that are going to sector 0. So for instance, the previous table, we had a row at time t4, a source 2 request, which was touching sector 1, 2, and 3, but not sector 0, and that row gets removed here. So other than that, this table is exactly the same with some additional information. So if there is a write, this table has additional information about what the write data is and what the byte enables are. So each sector is, in this sample example, 16 bytes. So it will have 16 byte enables and 16 write data. But for simplicity, we're showing just 2 bytes here. So this is the structure that will be fed to the system Verilog solver, and it will have built-in ordering rules, and the solver will try to see if we can reorder the rows of this structure to generate a global order. And if it succeeds, it will spit out that global order, and if it doesn't, then that means there does not exist a global order subject to the ordering rules. This slide shows the sample system Verilog solver output. For the example shown in the previous slide, the solver was able to find a global order. And so the randomization passed, and this was the output of the randomizer. So in here, you can see the rows which were previously marked 1, 2, 3 up to 9 has been reordered to create the global order. So in this global order, every read gets the previous write data, which has a byte enable 1. So for instance, read 1, the previous write is write 2, all the byte enable 1, so x3 and x4 for the read was obtained from this write. You can see that this read 4 got one of the data from the prior write, but the other byte it got from a write that happened much earlier, and that's because there was no write with byte 1 enabled between this write and this read. Let me now try to explain at a high level how the solver would determine whether there exists a global order subject to all the ordering rules or not. To do that, the solver will take an input matrix I, where each row of this matrix is a memo, and the rows are in issue order. And then it generates a unique permutation of n integers called gorder using the code here. And then it will use that unique permutation of n integers gorder to permute the rows of the input matrix I into a row permuted random matrix P. We will assume that the memops in P, the rows are in global order. And later on, we'll write constraints to make sure that the rows of P are in global order. But for now, we assume that they are in global order and write ordering rules as high-level system Verilog constraints. And this shows a sample ordering rule where I and j are the row numbers in the issue order. And what this is saying, and by the way, gorder I and gorder j are the corresponding locations of the rows I and j in the matrix P. So what this constraint is saying is that if I is greater than j in the issue order and they have the same source, then in the global order also, and they are gorder I is greater than gorder j. This is another way of saying that memops from the same source must appear in global order in the same order as they appear in the issue order. So although this is a sample ordering rule, there are other complex ordering rules which like PCI ordering rules, which says posted transaction can pass non-posted, but non-posted will push out posted, or ordering rules involving strict and relaxed order can all be written in terms of high-level system Verilog constraints. So far, we have seen how we can write ordering rules as high-level system Verilog constraints, assuming the rows of P are in global order. But how do we write constraints to make sure that the rows of P are indeed in global order? And this would have been a very trivial problem to solve if all the rows in P were memops with single byte reads or writes, because in that case, the property for global order would be if row I of P is read, then it would just get the data from row I minus 1 of P. And it doesn't matter if row I minus 1 of P is read or write, this property would hold. And this is a property which is very easy to code in system Verilog. But the problem is that these memops are actually reads with multiple bytes, and there are writes that could have writes with byte enable holds. And because of that, this property that I just mentioned doesn't hold true. Because you can think that if row I is a read preceded by a row I minus 1, which is a write with byte enable holds, then row I, which is a read, will not get the write data for all the bytes from row I minus 1, because row I minus 1 has writes with byte enable holds. So how do we write constraints to make sure the rows of P are in global order in the presence of writes with byte enable holds? And there are several methods we found to do this, but some of them are more involved than the others, and not each of these methods are extendable to memops other than reads and writes. So in this slide, we're going to share one method which is the simplest of the ones that we found, and it is also extendable to memory operations other than reads and writes. The basic idea here is to create a random dummy matrix M, where the rows of M mimics the data of the memory after the execution of the corresponding row of P. And then once we create this matrix, then we will basically write three set of constraints. One, two between the rows of P and M, and one between the consecutive rows of M. So the first set of constraint, which is shown here, is all it's saying is that if row I of P is a read, then the read data is same as the memory matrix data for that row. The second constraint, all it's saying is that if the row I of P is a write, and let's say a particular byte J has byte enable 1, then the corresponding equate the corresponding data byte J to the corresponding byte in M, and do that for all J's. And this is what's shown here. So the final constraint says that if a row I of P is a read, then the data bit at this row I and I minus 1 will not change. And if similarly, if row I Pi is a write and certain bytes J have byte enable holes, then for those bytes the data won't change across the consecutive rows. And so with these three constraints, if we solve together, we'll make sure that the rows of P are in global order. And this separately, we have written ordering rule constraints. So if we solve everything together, we will see if there exists a global order subject to all the ordering rules. Now that we understand at a high level how stimulus batching happens and how BatchSolve determines whether there exists a GEO or not, let me just go over some of the more advanced topic which the rest of the paper deals with. One of them is atomic handling. The question is now, how do we take this framework and extend from reads and writes to atomics? And there could be different kinds of atomic: min, max, increment, decrement, compare, and swap. And there could be flavors of atomic which return data like a read, and some that don't. So the question is, how do we handle those atomics in this framework? The other thing that is particularly tricky is barrier handling in this framework. And although I won't go into all the gory details, I'd like to touch at a high level how barriers handle in this framework. So barriers are typically used in producer-consumer thread synchronizations, where it implicitly introduces a ordering constraint between reads and writes coming from different sources. So what the bats try to do is, based on the execution, it will try to find out these ordering constraints imposed by the barriers and then present that as constraints to the solver. So again, at a high level idea is, for every barrier, we will create a set S before and S after, and a memop can go into either S before or S after, or neither, based on certain sample rules. So for instance, here's a sample rule which says reads issued after the membar ACK. So if you issue a barrier and the ACK comes back, and any read that is issued after that barrier ACK from either same or the different source as the barrier will need to be ordered after the barrier. So it will go in S after. So using similar rules, there will be memops which will go S before. The idea is every element in S before needs to be ordered before every element in S after. So we can remove the barrier and draw direct edges. And so this computation or edge detection is done in the pre-randomized phase, and the edges are actually presented as constraints to the SV solver. And that's how we handle barriers in BATS at a high level. For those who are interested more, we provide links to EDA Playground, and we have created 2 demos. And the first one is a simple read-write atomic. We create one example of an execution for which GEO exists, and the other one where the solver fails because there does not exist legal global order. And then we have another link for demonstrating the barrier handling case. We developed and ran batch towards the end of the project, and we found that the initial development effort is 8 weeks compared to the POSS, which takes 80 weeks of development effort, which is a 10x reduction. Maintenance, we expect it to be nothing more than 0 to a week, because the method is immune to microarchitectural changes, and it's also very portable. If the test bench has some kind of scoreboarding, then these kind of bats can be easily ported over in a week. However, when we run bats, the test runtime and the sim time both increases by 10 to 15%. This is caused by the solver runtime and also the batching scheme. In conclusion, I would like to say that BatchSolve provides an interesting technique which is extremely low cost in terms of development and maintenance. It's highly portable, and it allows us to specify ordering rules as high-level system Verilog constraints, which can be very useful if you have memory operations going over a variety of links which have different ordering rules like PCIe and VLink and so on. However, due to the batching scheme, there's some slight loss in coverage and a slight increase in runtime. In future, I'm interested in seeing if we can reformulate this problem as a convex relaxation problem and use convex solvers to increase the batch size beyond what SV solvers can support. Thanks for listening to my presentation.